All right, thank you for joining us. Welcome to another episode of Scientifically Simple. Today we're going to be talking about propane dehydrogenation technology. And then a little bit of backstory. So when Mom and I first met at our previous employer, he was actually and probably still is the leading expert on this technology, amongst other things. So kind of as a framework, as we discussed previously, our plan is to kind of get into the weeds of engineering, the finer details of things that get missed, such as things like valve sizing, heat exchanger selection, ancillary equipment, things like that. And we decided to kind of use this as kind of like the header technology to discuss, since there are so many different components in this technology. But today we're really just going to do like a high-level overview, explain the process and some of the different innovations that exist today. Without further ado, I'm going to turn it over to my colleague.
Thank you, Brandon. So as Brandon highlighted, propane dehydrogenation is pretty much, as the name implies, is an alkane going to alkene. In this case, we have propane turning into propylene after removal of hydrogen. And historically speaking, propane dehydrogenation has been preceded by butane dehydrogenation, which turns butane into isobutylene, which has been used to upgrade the octane number of gasoline. So there's just like, for a historical fact, it's just a continuum in that sense. So as we are heading already into Christmas, we just wanted to be like introducing a picture of our team, given the spirits of these
really
wonderful
excited.
days.
Yeah. You want to show the team?
And here we go.
Okay.
So as you see there on
Is
the
that
far
the team?
left,
Okay.
yeah, that's the whole team.
It's like you're really taking this seriously.
Absolutely. On the far left, that's Brandon. And he's just like, the dude that basically takes care of editing all these videos and clips, and huge support for the engineering curriculum like we are presenting.
Hey, who's the handsome guy on the right?
And the far right, that's the tech genius. That's always like whenever we have an issue, and he's happens to be still just like he didn't even graduate engineering, and he's like a technology genius. That would be James. The evil Santa down there is like me, Mo here. So
thank you for taking it seriously. The rest of us took very professional pictures, and you showed up as evil Santa Claus.
Absolutely. I just like want to be like, having embody the spirit of these days. So thank you. So anyway, starting with the material, as we were talking about earlier, propane dehydrogenation, as any other technology, is going to be like having different partitions. There is the reaction partition, there is the conditioning, and there is the distillation and recycling, or basically, if we wanted to call it, it's the separation system. Reaction, that's pretty much the core of your business. I need to get this product out of this raw material. Conditioning is pretty much like, we know that you're never going to be having 100% conversion of your raw material. So for the propylene production, as the name implies, that's pretty much like the kitchen of the whole system, where you are making propylene from propane. That section is pretty much like goes to almost 40% conversion of propane to propylene. 40% of propane goes to conversion, and the selectivity is somewhere between 80 and 90%. Because like at the end of the day, we want to make propylene. That's our main product, and as the technology, the name implies, it's an on-demand process, propylene from propane, which is a whole different technology, away from steam cracking and naphtha cracking, where basically propylene is a byproduct of cracking oil or gas. So these are type of processes that I need to target production of propylene. For the conditioning section, that's where I have all these different components in my system, and I need to separate, pretty much condition my raw gas to send it later on for separation. Then later on, when we go to the separation system, that's where you need to separate your raw material, and it goes back to the front end of the plant, because that's what you buy money for. That's pretty much. And you need to get your product, which is propylene, to be at a given product spec. So that's the purification process. And the third part is like whatever that's not propane and propylene, you're gonna have to take care of it one way or another. Either it's gonna be used as a fuel, reduce your fuel consumption, or you're gonna end up like sending stuff like, for example, hydrogen to be sold if you are in a place where hydrogen can be sold to another customer, for example. So that's an overview of the whole PDH technology, and it's basically those three sections that represent that chemical plant. So in a nutshell, like if we wanted to be like a little bit zooming into the PDH technology, as you can see it here, we have the depropanizer section. That's where like you're getting your propane feedstock. Normally, that's coming from an upstream vendor that basically separates propane from natural gas. So propane is highly likely is not going to be 100%. There might be have some butanes and pentanes, hexanes, etc., and you need to purify that. That's where the depropanizer is, and it pretty much like separates the C3 as an overhead product, and that goes to your PDH reactors. The bottom products, which is like gonna be C4 plus, it will be used most likely as part of your fuel system to reduce your natural gas. Once go to the PDH reactors, that's where like your main chemical reaction is turning propane into propylene and hydrogen. However, as in any chemical reactor, nothing goes to perfection in a single reaction.
One of the things that was really cool that I was not aware of is that there are so many different variations on this one step. So what you'll see, and it is the technology comparison, all these different, and they're called licensors, right? They own this technology. They all have a different spin on how they actually achieve this reaction, which impacts all your downstream equipment and how you design those processes. So I just wanted to go ahead and say that now.
Yeah, absolutely. That's a good point, Brandon. So that pretty much like is going to be the bread and butter of each of those licensors, but like overall, pretty much their core, the core work, the core like how the physics of the whole process is pretty much the same for all of them, and we are going to be going to details in the technology comparison of different licensors. Downstream of the PDH reactors, you're gonna be like having, of course, again, like in the reactor itself, beside the propylene and hydrogen, propane can be cracked, and instead of like at the carbon-hydrogen bond, it can be cracked at this carbon-carbon bond. And if that happens, you are gonna end up like with methane and ethylene. If ethylene is produced, you're gonna like eventually meet some hydrogen and turn into ethane. So pretty much this is the mixture of the different components that you can find inside the reactor itself. If you end up like having some type of dilute, like using steam, or for example, you might end up like having steam reforming happening, and that can produce carbon dioxide. And for the sake of generality, we are going to talk about like also the fact that carbon dioxide is part of the side products that can happen from this reaction. So downstream of the PDH reactors, you're gonna definitely have propane, propylene, hydrogen, residual methane, ethane, ethylene, and carbon dioxide. Now the whole role of the reactors are done. Now it's gonna be a matter of conditioning. So the first conditioning, I need to take care of the temperature. Before I go to the separation system, I need to get my raw gas into a given temperature and a given pressure. In the waste heat recovery, that's pretty much as the name implies, I utilize the hot gas to be preheating different streams within the process that needs to be preheating while cooling my main process gas. It plays two roles. It basically conditions the gas and reduces the overall utility consumption and the size of utilities I have. Then I go to process gas compression. That's where I take care of the second component of the conditioning part, which is pretty much the pressure of the system. Once you have the correct pressure and the correct temperature, now it's a matter of distillation. We have a stream that's mainly hydrocarbons. The only thing that's odd in that is pretty much the carbon dioxide and the hydrogen. So the first system that you go to is the deethanizer. And the deethanizer there is pretty much, as the name implies, remove anything that's lighter than C2. So it's going to be ethylene, ethane, methane, carbon dioxide, hydrogen. All these guys are removed from there. The bottom of the deethanizer stripper or the deethanizer column itself is going to be the propylene and propane. That goes to the C3 splitter, or basically the propane-propylene splitter, because like both of them are C3s, but it's an olefin versus an alkane. Now, in the C3 splitter, you're gonna need to do two extremes pretty much. You need to purify your propylene to almost 99.9+% by weight, and that's what the specs of the propylene product has to be if that's going to be used as a polymer grade, which majority of propylene is being used for. If we're talking about a polymer grade, it's going to be 99+%. If it's a chemical grade, it's going to be 90 to 95%. If it's a refinery grade product, it's going to be 70% to 90%. And that's of course like it, every grade has its own type of price. The highest price as you would get from there is like the polymer grade would be the most expensive part. So pretty much like what dictates the grade is what is being used for. So if there's going to be going to a refinery, they can be fine with 70 to 9%. If it's going to end up being used as a chemical grade for any other production, like for example, if I'm making acrylonitrile, they can be okay having low purity kind of propylene. But like in terms of I'm making directly a polypropylene, which is the second biggest polymer on a global level, it has this kind of like spec that needs to be 99+% by weight. Now regarding the propane itself, and the other chance, propane is going to be sent back to the battery, like to the front of the plant. So you don't want to be like sending any propylene all the way to the front, because it's going to impact your equilibrium. If you have like product, it pretty much slows down the propane conversion. That's number one. Number two, you're destroying your product that you worked so hard to make in the first place. So that's why recycled propane has to be as pure, and that's why the propylene product has to be as pure as it should be. And from those two facts, you would imagine how that C3 splitter is gigantic, because not only it has to be providing two different streams at high purities, but on top of this, it's dealing with two products that the relative volatility is insanely small. So you can imagine how many separation trays that you're going to need to be having in that unit. And on top of this, the amount of reflux ratio that's going to be on top of it.
So to that point,
yeah.
So this is a distillation column. Can you kind of give like a very high level overview on what a distillation column is and how it works?
So a distillation column works on the principle of how volatile a given product to another product. So if I'm talking about like something like methane and butane. Methane and butane, you would look at the boiling point of each of these components, you're going to find that the methane is so way more volatile than the butane. And the bigger the distance between those boiling points, the smaller, the more compact the amount of trays I'm going to need in order to separate them. The closer these boiling points are get to each other, basically the difference between them gets tight there, the more trays I'm gonna need. So that's number one. That's the basic thermodynamic principle, is that I need the closer the boiling points, the harder it gets. Or basically, that I need more separation unit in order to separate them. That's assuming ideal behavior. If we are talking about isotopes or something, that's going to hold different discussion. Now, in our case, propylene and propane, their relative volatility, or basically their boiling point, is super close. We are talking about like the C3 splitter operating pressure, for example. You are talking about like almost 2 degrees difference between the propane boiling point at pure conditions versus propylene at pure conditions. That's how tight it is. Even on a molar mass perspective, let alone like forget about the fact that we are talking about two different functional groups. Like we are talking about like a pi bond, sigma bond versus only sigma bond. We are talking about like 44, which is the molecular weight of propane, and 42 is the molecular weight of propylene. So it's even like, even on a molar mass perspective, you can't segregate that. And of course, like, in the future, if there is a separation unit that can prove to be economically more feasible to separate those two components, of course, is going to be like replacing distillation column. The other component of the distillation column is the purity aspect. So the more purity I need to get my product, the higher the reflux ratio has to get. That means the operating conditions. I'm gonna have to boil and condense. I have to boil at the bottom and I have to condense at the top insane amount of these products or of these chemicals, because I need to purify them. So you would imagine that a boiler has to be operating at almost acting like I am dealing with a pure propane. So it's going to be always operating at that temperature. And the same applies on the condenser. The condenser is going to be always operating also at the propylene boiling point. Right. So that's where like the problem arises in C3 splitter. Is one of the extreme conditions of distillation. You need high purity, and at the same time the relative volatility is super tight. So that's just, we are going to speak about these in future episodes, about like when we go deep down into distillation and more detailed discussion about the propane dehydrogenation technology as well. So now getting back to the undesirables. The undesirables in this case is like, now anything that anything like ethane, ethylene, methane, hydrogen, and CO2, what's going to happen to them? First of all, I need to separate the carbon dioxide out of the system. And the reason why I need to do this is that carbon dioxide is by nature, as like many of you would know, it sublimes. There is a point it starts turning from gas to solid. And one of the separation units that we have a lot of aluminum heat exchangers, or like something like the cold box, which pretty much goes into very deep cryogenic temperatures. And if a solid CO2 would be forming in these cases, it will basically cause a huge damage and taking out that unit out of operation.
Yeah, so I'm not gonna lie. When we first started talking about this, it never even dawned on me that that's one, that would happen, and two, that's why you remove the CO2. It just didn't even cross my mind.
Mm-hmm. Yeah. So unlike in a typical ammonia plant or a fertilizer plant, there you need to purify CO2 because of it's a oxidizing agent, and I need to get rid of it before going to the converter. In here, it doesn't have any purpose beyond you need to separate it, otherwise it's going to cause damage, like physical damage in your cryogenic surfaces. So that's the carbon dioxide part, and that can be like so many there are so many solutions out there that can take care of that. We don't want to be going into so much depth about it, but mainly they always use the activated MDEA solution, which is amine solutions. That's basically almost doesn't take anything from the process gas beside carbon dioxide. That's the most thing that's highly selective to. Now, methane, ethane, and ethylene, they are going to be distilled out like normally, like the norm, and it's going to be like having the C2 is pretty much the ethane and ethylene as the bottom, and the top is going to be mainly methane and hydrogen. Methane and hydrogen is going to go to the cold box, in those type of cold surfaces, cryogenic surfaces, methane is going to come out as a liquid. There is no way hydrogen is going to ever go out as a liquid, because like hydrogen pretty much, if you look at the phase diagram of hydrogen, it's almost like exclusively exists as a gas phase.
So you're telling me there's a chance?
There is always a chance, but it's not going to happen currently. It's never gonna happen on a commercial asset, but like pretty much like there are definitely some applications for it, but when we're talking about like chemical applications, no way, unless you are deliberately need to do that. So that's pretty much how hydrogen is separated from hydrocarbons. All your hydrocarbons, which is basically ethylene, ethane, and methane, goes as a tail gas to the fuel system, and that's that's the best that you can do with them, because they're pretty much, that's what natural gas composition is. They are like methane and ethane and stuff like that. Hydrogen, that's a whole different story. And the hydrogen product that you're making, it's going to be highly dependent where that chemical plant is going to be located. If I'm going to be located in a chemical hub close to a refinery, is he probably going to buy it from you at whatever spec that you're gonna need, probably like low spec, because normally in refineries you use it for hydrotreating or type of applications that doesn't require high maintenance or high spec on how pure hydrogen is. But if you're gonna end up like being in a chemical hub where like you're located somehow close to a fertilizer plant, whereas you are making ammonia, for example, well, you're gonna be like telling you I need very high purity product. And that, of course, is going to be dictating, as a customer, what type of separation unit you're going to put there. Is it going to be a cold box? Is it going to be pressure swing adsorption, or any other thing? So it's going to be like always this kind of like economic trade-offs, like what the customer that's going to take that hydrogen willing to pay at which quality versus how much you want to be investing in what unit, and if it makes sense business wise or not. If you don't, there is also like a third option where like you might be located to a hydrogen network. There are actually like a hydrogen networks, like pipelines, where like you might end up like have to purify that hydrogen and pump it into a main network of hydrogen pipelines, like you would see around Texas, for example. This network basically, it's a like almost like veins, like blood veins in a human body. Is like you have it there, and whoever gonna need it's gonna be taking it from somewhere. If nothing of this is available, unfortunately, the customer gonna probably use the hydrogen to be burning it and turning it into fuel, which is like the worst thing that you can do. But like if you're not gonna emit hydrogen to atmosphere. So that's pretty much the short introduction about the PDH technology.
I had no idea, and I mentioned earlier, there are so many different variations on this one process. And a lot of that is captured in this slide, in this table. And it really is just insane that there are so many different ways you can attack the same problem. But then the obvious consequence of that is highlight there, feed propane to metric ton of propylene. That's the result, right? Like that's what we as customers care about.
Yeah, pretty much like the core physics is the same. You are pretty much taking propane and turning into propylene and hydrogen. That's how it goes for all of them. Some of them are already have been commercialized. Some of them has already a lot of big history of commercialization, like UOP. Some to a lesser degree, some they like have way less, like Lamas and ThyssenKrupp, for example, and some are still like even on a pilot on a lab scale, like type of like still a research and development kind of like level. So that's way of actually like trying to separate them. There is other way too. There is some operations that are normal like always continuous versus cyclic. So as we have highlighted earlier, propane dehydrogenation has lots of side products, and one of them is carbon, and carbon doesn't go with the raw gas. It tends to be like basically settling on the catalyst. UOP, which is the oldest technology, basically have a residence time for the catalyst, and as you know, the catalyst is flowing through their tube or through the reactor, and it leaves the system, goes to be regenerated by blowing pretty much air on it to combust the carbon and basically get recycled back. And that's a big deal because pretty much that makes the reactor as small as possible, because you don't need to account for the downtime when you need to regenerate the whole reactor in the first place.
And I'm glad you said that. That it didn't get said on the previous slide, but if you can imagine, these facilities are massive. I don't know if you can give us an idea of like the scale of something like this.
Oh yeah, I mean like in a typical like a plant like that. I mean it's very expensive reactors, because like we are dealing with whether it's deep vacuum or high pressures, or we're dealing with like hydrogen like embrittlement or something like that. So pretty much like everything around that plant is pretty expensive from the front to the back, and the economics of this process depends heavily on the how much I'm buying propane versus how much propylene I am selling it at. And propylene and propane are not tied together. Propane is basically dependent on natural gas price. Like propylene has nothing to do with propane. It depends on crude oil, and because it's mainly coming from that direction. So if propylene price goes down, your margins are, you pretty much you can go very easy into a negative cash flow. So pretty much like the economics of the process, whether it's operation cost or capital cost, is dependent on the difference between those two. So that's where all these licensors are playing. The core is like, I need to, some of them is going to be like saying, I want to focus on the conversion. Some of them, I want to be focusing on the capital expense itself. And they are doing this either through the mode of operation or the type of catalyst, or like operating conditions, which we're going to be like highlighting. So you have two main catalysts that we're dealing with. It's either platinum along with tin on alumina, or chromium oxide. It helps a lot with like chromium oxide. It helps a lot with conversion and selectivity, but the chromium oxide unfortunately have a lot of toxicity and problem with emissions. So that's why like it gets a bad vibe out there, like in terms of the APA. Platinum tin has less yield or less selective than chromium, and the reason why platinum is like doesn't distinguish between like cutting carbon versus carbon hydrogen, and that's why we tend to be like putting tin there. And the whole purpose of tin there is pretty much work around the electronic configuration, or basically in a simple term, just make the carbon hydrogen bond more selective to be broken, not the carbon.
And the catalyst is the most important part, right?
Yeah, absolutely. Catalyst plays
I was
a
just
huge
kidding with
role.
you because of your catalysis class.
Catalyst plays a,
throwing it up for you.
Yeah, I mean, like catalyst is not, it's part of the overall thing. It's a reactor design. Catalyst is one of the factors out there, but like it always at the end of the day is gonna depend on so many things that's happening. You have residence time, you have
right
pressures, temperatures.
Yeah, no, I agree with that.
The thermodynamics that you're working with, and this we're going to be highlighting in depth in later episodes. Like we said, like you have different licensors work around different operating conditions. So you look at UOP, for example, they work with hydrogen. They use the inert. No, it's not an inert, but they use like they co-feed hydrogen with propane. And someone in the first glance would be like, oh my goodness, like why would you feed hydrogen with propane that actually gonna start like slowing down your reaction because it's an equilibrium? But like the actual like there is a given amount of partial pressure of hydrogen that you need there, that it will be retarding the carbon formation. So they are playing this kind of like trade-off between how far I can slow down the reaction versus how much I'm slowing the reaction of carbon formation. So which one is being slowed more? So now we're talking about kinetics. In case of llamas, for example, they are using vacuum. It's propane, but deep vacuum. And as you would see from the thermodynamics of the problem, we have one mole or one molecule producing two molecules. We have one propane producing one propylene and one hydrogen. So the problem there, thermodynamically speaking, is that in order to increase the conversion, I need to reduce the pressure of propane, or the partial pressure of propane. That's pretty much like what llamas did. Is like in terms of like absolute pressure, which is like the total pressure, and happens to be the pressure of propane. They pretty much operated at vacuum. And of course, because of the fact that you're pushing conversion there, and the residence time is a matter of minutes, you can imagine how hard, how expensive those reactors are going to be, because you are swinging between regeneration and normal operation in a matter of 15 minutes. So it's a pretty tough service. It's a highly deep vacuum, so you can imagine the operating cost associated with that to actually maintain and spend all this amount of steam on injectors to maintain the vacuum. Now, ThyssenKrupp come up with another idea. Is like, okay, let me focus on the partial pressure of propane, but still maintain the total pressure. So the total pressure is still going to be above atmospheric, but the partial pressure is of propane is basically reduced by presence of steam. But there is a drawback from there. You get like the conversion that you need, but unfortunately, the presence of steam is going to be promoting another reaction called steam reforming, which is very familiar if you are dealing with steam reforming of methane. Here we have steam reforming of propane, which that's where the carbon dioxide, for example, comes from. So those, all of them are going to be like telling you, hey, my catalyst is like 4 years or something like that. But at the end of the day, what matters in the end of what will matter for every customer is not just like how long the catalyst life, it's like how that activity of that catalyst looks like across that life. Because like if I'm having an active, like the catalyst
that is
is
an
like,
excellent point. Yeah, no, that's a great point.
because like, yeah, I mean, like
yeah, you're right.
I can live with 50% activity, for example, like let's assume that, but like, does it take like an exponential, like going from 100% to 50% across the 5 years in an exponential decay, or is it linear? Because if it's linear, you could probably say like, I will take that, or even like even better if it's parabolic, like if it basically it slowly goes down and then suddenly just once it gets to a specific threshold, it just breaks down almost immediately.
Right.
So that's another perspective that like customers need to be always looking at, because like it doesn't matter like if I'm saying like a catalyst can be working for 4 years or 5 years, is it going to how the activity of that catalyst looks like, the activity function of that catalyst looks like, and you have to be 100% sure the activity of catalyst is never going to be 100% throughout those 4 years. Because that catalyst, irrespective of which technology that we're dealing with, all of them mix carbon, and all of them have to be combusting that carbon using air. So it's a very highly exothermic. So the chances of having a local temperature spikes where like centering or kind of like permanent destruction of those active sites is going to happen. So do not expect 100% across the whole 5 years. The OP, in our case, it uses fluidized bed, as we mentioned earlier. The reason why we have a fluidized bed, typically fluidized bed are used whenever you have an operation or a reactor that not only the process leaves the reactor, but you also have the catalyst leaving the reactor. And that's the nice thing about UOP. It makes sure that it has the smallest reactor size for any of the technologies that we're having. So the catalyst continuously leaves the reactor itself, and it goes to be regenerated in a different vessel and comes back. And in doing so, it's a continuous 24/7 kind of like process. all the other commercial versions are fixed bed, which means whatever reactors that you're going to have, not all the reactors are going to be 24/7 at the same time operational.
Right.
One or more are going to be like in some regeneration sequence while the rest are in operation. And that's the problem with these kind of fixed bed reactors. They are way simpler in their design, but like they come at a very high cost in terms of the reactor design itself, because you're going to have to create a volume to overcompensate for the downtime for the regeneration sequence itself. So that's pretty much like the difference between the fixed bed and fluidized bed. But like again, all of them are focused on making propylene from propane. But like the bread and butter of each light sensor is like how to work their kinetics, all laws of physics that we have, in order to be getting the minimum total cost, whether it's like minimum capital, or minimum operating cost. The biggest key performance metric of this plant, as we discussed earlier, is something called utilization factor, which is basically how much propane I'm using to produce 1 ton or whatever, 1 mass unit of propylene. It's mass unit. The cool part is like, because the molar mass of both components are the same, almost the same, you can get by, and instead of like saying a molar ratio, you can have a mass ratio. So it, we can kind of let that slide in that case. So that's in a nutshell the difference between different light sensors, and the different ingredients, or how like they are playing with laws of thermodynamics and laws of physics in order to be, manipulating their way in order to make that propylene from propane with the minimum cost out there. Would you like to be?
Yes, let me introduce this. This again will be the first and last time that I get to speak. So, pulling back the curtain, Muhammad and I do talk offline about how we want to present some of these different topics and what to actually cover in those topics. And so, one of the things that we started talking about was, and really it was me, right? Since we were talking about was, what could be done to improve the process. With him being familiar and him being years removed from it, is there anything that you look back and it stands out and it's like, we missed this or we missed that? And so he did prepare these graphs, and I asked him about putting them on the slide so that we could discuss, and we really can't go into specifics right now, but the top green graph is the design basis for these types of processes, right? And me, with my simple mind, I'm going to say it's basically a straight line. Now, obviously, it's a plane, no duh, but it's basically straight. The bottom graph is reality, right? And if you start to follow those lines and the axes, that more or less resembles what was just described in terms of the technology comparison. And the reason for the difference and what is missed, and kind of something that we hope to highlight with these videos, is the significance of your fundamentals, right? Thermodynamics, transport phenomenon, and then in this case, equilibrium, right? Mm-hmm. So as we're taking propane and making propylene, we're not just making propylene, we're making all these other materials. And the top graph assumes that there is no interaction effect with those other materials. And the bottom graph is produced calculating those interaction effects and what the impact actually is. All right, I'm done. I'll shut up now. I'm just going to listen and learn too.
Yeah, absolutely. Absolutely. Perfectly said, Brandon. So pretty much like, the first thing that happens before we even like talk about catalysis, and we start by like talking about like what type of catalyst is working for this type of reaction, the first thing that has to be highlighted is the chemical equilibrium. And chemical equilibrium is way more harder than physical equilibrium. Like, for example, if I'm talking about like separating benzene from toluene, it's already taken for granted. I already have two components, and those two components are already known, and the only thing that's that differentiates them whenever I'm doing any separation is the relative volatility. When I'm talking about chemical equilibrium, I have to know beforehand, like whenever I'm running this reaction, what kind of ingredient, what type of components or products is going to come out of this reaction. So I cannot be like assuming like, hey, I'm going to be working around propane dehydrogenation and I'm making propane from propylene. Let's like now run our chemical equilibrium and see like how the conversion of propane looks like for that single reaction from Gibbs free energy kind of approach for chemical equilibrium. Why? The problem is like if we do that, it's going to give us the wrong impression which temperatures and partial pressures of propane I'm gonna need. Now, if I'm that, what does that mean? If I run the reaction and I find only propylene and hydrogen, and before I run that reaction, I already like worked my thermodynamics that's only propane and propylene and hydrogen, and find that's consistent. Yes, that's perfect. Now you need to work your way around the catalysis. But if I'm already like running my chemical reactions and I find myself like I'm producing methane, ethylene, and ethane along with propylene and hydrogen, then the thermodynamic picture that was created initially is wrong. That's when we need to be going back and doing the same chemical equilibrium function again in order to get the correct map thermodynamically speaking. I need to look now how the temperature, what's my favorable temperature, what's my favorable partial pressure of propane that I'm going to need in order to maximize the propylene. Because now I'll be able to be like saying, like, hey, I already know I'm going to have methane, ethane, and ethylene and propylene. Does the previous picture align with the new picture? If so, okay, great, no problem. Now you can start working on your catalysis and kinetics and all these experiments. But if that doesn't align, then what's going to happen is pretty much the catalysis and kinetics are going to go in a whole different domain of temperatures and pressures that you could have just saved yourself the effort and the money spent around that by just revisiting that same function. So what kind of like side effects that can happen on your system? Beside the fact that you go into the wrong domain, you could actually like whenever you go back to that map, you can already see that the thermodynamics itself can be leveraged to maximize the yield of propylene. I don't need to start designing the catalyst to be having the support along with the support. Like the problem gets more complicated for no reason. You might actually from the get-go find out like, hey, oh my goodness, like, thermodynamically speaking, this kind of like temperature domain, the new one based on the mixture of the products that has been validated in the lab, is now telling me that if I operate in these temperatures, those extreme temperature previous known to us, now the thermodynamics is telling me like the yield is going to be maximized or the selectivity is already maximized. Now, the catalyst, all it needs to focus on is conversion. It doesn't need to focus on like conversion and the selectivity. So this is the problems that will be arising with thermodynamics versus kinetics, at which point the thermodynamics delivers to basically have that milestone to move to the next step, and at which point where you are actually like finding out something in the lab that you have run an experiment that basically makes everything that you have done thermodynamically speaking invalid, and you're gonna need to be like doing trial and error or iteration. You're gonna need to go back to the same function that you have done previously that assumed a single reaction and run the same thing again to be actually finding out how those chemical equilibrium is going to look like. And as you see from those two graphs, if I introduce something like, for example, steam, here is my total pressure, here is my partial pressure of propane, here is my yield. Now you look at the same yield for propylene for the simplistic view versus the actual view, you find out like the picture doesn't look the same at all. You're gonna find yourself, the partial pressures are going in a whole different directions than the simplistic view. And it actually gets worse, like if we're talking about like temperature wise as well. And one of the biggest aspect in terms of equilibrium in this kind of reaction is that we're gonna find out like the simplistic view of single reaction pushed everyone to basically focus on the 600 plus C. Because like the thermodynamics of the first graph, the top graph we have there is like telling you like, hey, if I want to be having high selectivity or high yield of propylene, I need to push my temperature in that direction. But in reality, when you look at the mixture and you redefine that function for yourself again, you find yourself like you are in the wrong domain. That the whole catalysis and the whole R&D should have been shifted into a whole different domain, and that's the critical part of understanding the thermodynamics issue itself. I can just like run. Yeah, go ahead.
So I was just going to jump in real quick. If I can just make two comments. So one, right? So the foundational work for Muhammad's PhD is around this concept, right? Having built out a whole process around an idea, and the foundations for that idea are flawed, which is the same as what happened when we worked together previously at a previous employer, where we had a whole process built around a foundational idea, and the foundations were wrong. And again, going further back, at my previous employer, I had all these different processes that I ran, and in every case, my equilibrium, my guide looked like the top graph, and we had no ability to produce the bottom graph. But the bottom graph is what we actually saw, and the question was always like, well, why doesn't it look like the top graph? And I'm just saying that just so for anyone out there, right, that's kind of why these things matter. And it's not to say that they're simple or easy to produce, but there is a physical significance to it. And just kind of discuss it a little bit further, right? So at the previous employer I'm referencing, when we looked at this process, we looked at the foundations, and when we understood that the foundations were wrong, we took, for me, because I was running the line at the time, a reaction that took about 2 hours to run and was very difficult, and we ended up running it about 20-30 minutes. I mean, that you remove 75% of the time. And that's not to talk about the energy or the capital cost or anything else that came with it. That was just time, 75% gone. And that's without any other tweakings. That's just figuring out that my graph actually looked like the bottom one, it wasn't the top one. And the same can be said for Muhammad's PhD and the work that he's doing, right?
Yeah, absolutely. So I mean, in general, that's how like, how can I say that? How like understanding the fundamentals of thermodynamics is critical, because it's like almost like a GPS. If your
right.
GPS,
yes, good, that's well said.
If you put the GPS wrong, you're gonna end up being located in the wrong place. You're gonna be wasting a lot of gas. You're gonna be wasting a lot of time on something that won't happen. So that is the criticality of this. I understand like there are so many technologies that, like, you know, if we're talking about like something that's pretty new, like, you know, in bioengineering, for example, or something like that, yes, there might be like something that we are exploring in a new frontier. But like in general, this is the iteration that we have to go through. You start with an assumption, you run the thermodynamic analysis about this, and we are talking about chemical reactions. And chemical reactions, the tricky part about it is like you have assumed a given set of products. And given that set of products, you worked your equilibrium and you started to be like saying, hey, here is my GPS, here is my temperature, here is my pressure, etc. Here's my state functions, pretty much. The critical part of this, you're gonna need to verify it, because if you don't verify that and you start working on, you jump into the lab and kinetics and all these things, the high chances is if you don't get back to confirm what you have analyzed previously in thermodynamics, most likely you're going to be wasting a lot of time, a lot of energy, a lot of expenses on the wrong coordinates. You are working with temperatures and pressures that basically keeps like telling you, hey, I keep getting this bad yield. And the problem keeps getting complicated. Why? Because you're gonna now start to be like looking into how I can make that catalyst or that enzyme more sophisticated, more complex, and it's going to start to be like, you know, running out like a snowball effect. The problem creating another problem. And if you looked at it from like an iteration perspective and you revisited what has been done previously, that would have probably simplified the path from the beginning. That doesn't mean like the end solution is going to be simple, but like in general, before you always have to be like having checks and balances between what's being run in the lab and what being thermodynamically assumed. So I cannot be like writing a paper about like thermodynamics of PDH and put a chart out there that basically shows a single reaction propane to propylene, and here is my temperature and here is my pressure, and that's why like we need to operate at high temperature. No, because like that chemical equilibrium did not take into perspective the different type of components that we have. The other part I need to be adding as well is like I can't look at different light sensors and assume the same mixture. Like for example, if UOP is like introducing hydrogen in your system, you are gonna find out that the chemical equilibrium distribution in their chemical reactor at the same exit temperature is different from Lamas. Why? Because they introduced a reactive ingredient into that mixture. So also that's another part that we always have to put in perspective. If I added anything into my system and assumed it's inert or dilute of some sort, I need to verify it's doing as such. If it's not, then I'm gonna need to re-establish that equilibrium as well. This is the type of iterations. It can be like in the beginning, pretty much it has its own complicated calculations, but like redefining that is very critical, because that's going to be telling you like, here is my boundaries, or at least my favorable boundaries that I need to work my catalyst design of experiments around. Otherwise, you might find yourself like in a whole different domain, and it's a snowball effect. The catalyst keeps like saying, like the catalyst telling you, here is my distribution, and you are thinking that the selectivity is based on the catalyst needs to be upgraded, but in reality, it's literally the thermodynamics is telling you it has to be that distribution. So you might be actually in a thermodynamic equilibrium, and you're not even noticing it.
That is really well said. I didn't even think about that. That is really well said.
So we are going to definitely go into so much depth about that in later episodes as well, into the thermodynamics of the traction and potentially the kinetics of the tractions. That's just like to be giving today an overview of what's a PDH, what it's about, what it does, and stuff like that. But anyway, like before in our next episode, we are going to be discussing something like, all the engineers out there, whether it's undergrad or just new grad out of school. We are going to be talking about topics about like what's an EPC, what's an EPC project, what's an EPC contractor, what's a project engineering timeline, and what's the sequence in there, what happens in there, along with what project engineering execution looks like, how different disciplines of engineering looks like, how different disciplines between engineering versus procurement versus construction looks like. And we are going to be going, of course, into our bread and butter part, which is like within the chemical engineering part or process engineering part, how the working steps looks like, how like documentation wise a process engineer would go through whenever a project is taking place, or even in the least part. It's like what you should be expecting, even if you're working in an operation plant, what type of document you're dealing with. And that's pretty much like what we're going to be discussing in our next episode. Just like, please stay tuned for that. And this is pretty much like an overall picture for what we are going to be discussing. Like, an APC is an engineering, procurement, construction, and the APC contractor or contractors plans and execute all these projects before turning them into the customer as a finished, pretty much like, chemical plant to be operated. Like pretty much like whenever you're buying your car, there is GM or Ford that basically assembled everything. So pretty much like GM and Ford can be looked at as a contractor, and it is your car. Now you can just drive it. That's pretty much like how it looks like in the chemical industry, but in a way more complex way. So please stay tuned, and there's gonna be lots of material that we're gonna be discussing there, and we are looking forward to be hearing about your comments and your feedback. Thank you.
For those of you watching today or listening wherever and however you're enjoying, we just want to say thank you again. We really do appreciate you taking the time. Hopefully you've learned something. Hopefully you've gotten something of value. Like we said, this is just a very high-level overview of a process that we hope to use as an example to delve deeper into some other critical topics. If you like what you heard or saw, please send an email to sciencemadesimple@outlook.com. Leave a comment, leave a review, leave a note, and just kind of let us know what you think. We're always trying to get a feel for what we're doing right, what we're doing wrong, what we can improve on, as well as other topics to cover or other gaps in industry, things of that nature that you might find interesting. Find us on YouTube at Scientifically Simple, and that's about all I got for today.
Thank you, Brandon. Have a wonderful day.